Assalamu alaikum everyone. Today we have to continue with this chapter number 9 and we will mainly talk about the cash flow diagrams and we will see that what are the different types of cash flow diagrams that we can see in the industries. So the cash flow diagrams, it represent timings and approximate magnitude of the investment on the cash flow diagram. So it will give you some idea about the cash flow within the industry or any plant or in any business. X-axis is time and y-axis is the magnitude. Magnitude means that what is an amount of money, and x-axis it can represent you the time. Both positive and negative investments are possible. So investments can be positive and negative depending on the investment type. Okay, if you are taking some money, if you are borrowing some money from the bank, so maybe it could be positive at your side, but it could be negative at the bank side. Okay, so you have to see who is the buyer and who is the lender. Okay. In order to determine direction sign of cash flows, we must define what system is being considered. Okay. So when you have to consider the cash flows, we have to see what system you are being considered. Okay. Now the cash flow diagrams, it can be divided into two parts or two different categories. One is a discrete cash flow diagram and the other one is a cumulative cash flow diagram. Now what is a discrete cash flow diagram? Now if you look at this figure here, this discrete cash flow diagram, it provides you a clear and unambiguous pictorial record of the value. Okay, so you can see different values here and it can give you some information on the time in terms of years on the x-axis, okay, during the lifetime of the project. So what you can see here, payment for each of the year, it can be shown independently. For example, in the year 1 you have $1,000 and then in the year 2 you have $1,200 and the year 3 you got maybe $1,500. Okay, then in year 4 nothing happened. Then in the year 5 you spend $2,000 and in the year 7 you have to estimate what is the rest amount of the money that you need to spend or you need to return. Okay, so it depends who is taking the money and who is spending the money. Now here you are taking the money at this point and you have to return the money at this side. Okay, now let us solve this example. I borrow $1,000, $1,200 and $1,500 from the bank at 8% per annum effective interest rate at the end of year 1, 2 and 3. Okay, so you would get the money $1,000, 2 and 3, $1,200, $1,500 at the end of year 1, 2 and 3 respectively. At the end of year 5, I make a payment of $2,000 and at the end of year 7 I pay off the loan in full. Okay, so in the year 5 you return $2,000 back to the bank. Okay, and you have to see that in the at the end of year 7 how much more you have to return including all the interest rate. Okay, and the cash flow diagram for this exchange from my point of view, producer is given to the right. Okay, so from your point of view, you have got the money here in the 3 years and then you have to return the money in these years. Okay, now from the bank point of view, they have given you the money in this way. Okay, so they have given you the money in 3 years and they would get back the money in 2 years. Okay, from year 5 to 7. Now this figure is a shorthand version of the one presented in figure 9.2 earlier diagram used to indicate the cash flow diagram. Draw a discrete cash flow diagram for the investor. The bank represents the investor. From the investor's point of view, the initial 3 transactions are negative and the last 2 are positive. Okay, so this is the diagram from the bank point of view and this is a diagram from your point of view. The figure to the right represents the cash flow diagram for the bank. It is the mirror image of the one given above in the problem. Okay, so these two diagrams are the mirror image, but you have to see that who is taking money and who is like giving money, and you can like make the diagrams according to your deal. Okay, now let us solve another example. You borrow $10,000 from a bank to buy a new car and agree to make 36 equal monthly payments of $320 each to repay the loan. Draw the discrete cash flow diagram for the investor in this agreement. The bank is the investor. The discrete cash flow diagram for this investment is shown on the right. Okay, so bank is the investor. So bank invested $10,000 in the car and then you pay the monthly installment of $320 for the month of for the period of 36 months. Okay, now what we have to do, note there is a break in both the time scale and in the investment at time zero. Okay, now here you would see the clear break here. The bank will invest the money and then it will start like you have to repay the money, so you would see a clear break here. From your point of view, the cash flow diagram would be the mirror image of the one shown. Okay, so from your point of view, you would having the similar diagram, but it would be the mirror image where $10,000 would be on the positive side on the year zero, and then for the year 1 to 36, these $320 would be in the opposite side or in the negative side. Okay. Now let us see what is the cumulative cash flow diagram. Now the word cumulative, it will be very simple, that you have to add up what are the profits or whatever the expenditure that you are making. Okay, so cumulative cash flows, it keeps a running total of the cash flow occurring in the project. Okay, so you have to add up all the cash that is being spent in the project. Okay, and it will also give you some idea about the break even point. Okay, so at this point you are investing the money into the project, and at this point this will represent you the break even point, and after that you would have the profit from some project. Okay, now let us see from the example here. The yearly cash flow estimated for a project involving the construction and operation of a chemical plant producing a new product is provided in the discrete cash flow diagram given on the right. Using this information, construct the cumulative cash flow diagram. The numbers shows in the worksheet below were obtained from this diagram. Okay, so in the year 0, or just at the start of project, you spend maybe 50 into 10 raised to the power $4. Okay, so maybe I will ignore this units part. So in the year 0 you might have spent $50. Then in the year 1 you again like invested $75, and in the at the end of year 2 you spend more, invested $90 into the project, and from the year 3rd you like gain $30 out of that project, and from year 4 to 12 you gained $40 per year from the project. Okay, now we have to draw the cumulative cash flow diagram. Now there are two ways to make the diagram. First one, in the year 0 you invested 50 into 10 raised to the power 4. So here on the cash flow from the discrete side, you would put all the money that you spend or get from the project. So in the year 0 you spend 500,000, then year the 1 you spend $750,000, then year 2 you spend it $900,000, and then you get the positive income from the project. So you in the 3rd year you got 300,000, and from 4 to 12 years you get 400,000 annual. Okay, now if you want to make the cumulative cash flow diagram, what you have to do here, for the year 0 it would be coming 50,000. Now you have to add minus 500,000 with the minus 750,000, so overall it will become minus 120 50,000. So it will represent that how much money until the year 1 you have spent it. Now again for the if you want to estimate that until year 2 how much money you have spent it, so you have to take what is the closing of the first year, and then how much you spend in the second year, and then you take the addition here. Okay, so similarly you make this cumulative cash flow diagram by simply addition of the previous year amount of money, and you would get this graph. Okay, so once you have this graph, now if you plot this graph or these numbers according to the number of years, then you would be getting this kind of graph. Okay, now in the year 0 you spend some money, again in year 1 you spend some money, and at the end of year 2 you spend it minus $215,000. Okay, so you would see this one here, 215,000 dollars, and then it will be going like this way. Okay, so at the end of year 3, 4, 5, 6, 7. Okay, so in between the year 7 and 8 you would be getting some break even point. Okay, so this is the point where your investment would be recovered from the project, and after this period you would be earning the money out of the project. Okay, so this one is the way that how we can represent the project feasibility, and how we can actually estimate that what is the payback time of the project. So when cash flows occurs at different times, each cash flow must be brought forward or backward to the same point in time and then compared. So if you are making different investments in different projects, so and if you want to check which project is more feasible, then you have to keep the consistent time basis. Okay, so you have to just compensate the effect of time, because in one project if you invest money for the longer time, it would give you more return, or it depends on the project feasibility. Okay, so if you want to make some good comparison, you have to bring the investment at the given time scale. Okay, now let us see this example 9.13. The cash flow diagram obtained from example 9.10 for the borrower is copied below. The annual interest rate paid on the loan is 8% per annum. In the year 7, the remaining money owed on the loan is paid off. Okay, so at the end of 7 years, you have to return all the money, including the interest. Okay. Now, what we need to calculate here, determine the amount X of the final payment. So you have to see, calculate what is the amount X for the final payment, including the interest rate on which you have got this money from the borrower or from the bank. Okay, compare the value of X with the value that would be owed if there was no interest paid on the loan. Okay, and then you have to calculate the value that what should be the value of X if there is no interest on the loan. Okay. Now, how we can do this thing with the final payment of the end of year 7, no money is owed on the loan. Okay, so if you look at this one, after year 7, there will be no money owed on this one. Okay, because in this year 7, we have to return all the money that is with the interest that we have borrowed from the bank. Okay, no money is owed on the loan. If we sum all the positive and negative cash flows adjusted for the time of transactions, this adjusted sum must be equal to 0. We select as a base time the date of the final payment. Okay, so if we consider the final payment as the basis, now what we can do here from the equation 9.5 for I, now we have to see what is an interest rate. It is given here, it is 8% per annum, so that is 0.08. Now we have to simply use the compound interest formula. Okay, now this amount, the $1,000 that you bought at the end of 1 year, now how much time you kept that $1,000 with you? 1, 2, 3, 4, 5, 6 years, right? Because we have to estimate that at the end of 7 years how much you have to return. Okay, so the number of years you would keep $1,000, it would be 1, 2, 3, 4, 5, 6 years. Okay, so if you simply use the compound interest formula, so the final amount that is equal to the initial amount multiplied by 1 plus interest rate that is given to you with the power 6 here with the number of years that you would keep the money. Okay, so this is a compound interest formula that you can simply use, so that would be equal to $1,586. Now similarly, you have taken this $1,200 at the end of year 2, so how much time you can keep this money on the interest? 1, 2, 3, 4, 5 years. Okay, so similarly you would write 1200 here, and then the same way 1 plus this one is a percentage or the interest, then you can write this one for the number of years and you would get the new value. Similarly, you would do the same thing with the 1500. So you would keep this $1,500 or invest this $1,500 into the project for 1, 2, 3, 4 years, right? So you have to write down here with the power 4. Okay, so for each of the payment you would see that how much is the interest you have to pay at the end of the 7 years. So then you can add up all of these terms together, so that will become equal to $5,390. Now for the repayments, we have to estimate that what should be the value that you need to return at the end of 7 years. So how you can do this thing? Now we have to see that if you are having $2,000 at the end of 5 years, for example this one, if you have already returned some amount of the money, $2,000 at the end of 5 years, then you don't need to from this amount of money you have like already returned this much money, so you don't need to pay the interest for the rest of the year. So we have to compensate that effect. Okay, so $2,000 you paid at the end of year 5, so you would use the same formula on which you would not pay the interest, so minus 2000 plus 1.08 and then with the power 2, because we are now here. So for the 2 years we have to just negate the effect of the money that we have loaned from here. Okay, So here it will be equal to this one. Now at the end of 7 years, okay, at the end of 7 years we don't need to return any money, so the loan will be paid off. So the in terms of equation we can write $x could be returned at the end of 7 years. So f0, that is equal to minus x 1 plus 0.08 with the power 0, so it will be equal to minus $x. Okay, so we don't need to return anything. Now the total payment that you need to return here, you can add both of these two payments together. That will be equal to this one. Now the total amount of money that you borrowed, that is equal to that you need to return, that you calculated earlier by like compensating each of the amount for the end of 7 years. So that is this amount, and then you negate the effect of the two payments that you returned earlier. So you would be like subtracting this much amount of money from the total amount that you calculated earlier. So the total value for the X, it will be $3,058. Now we have to calculate, if we do not pay any interest on the loan, then what could be the value of X. Okay, so that is quite simple. So you borrowed 1,000, 1,200 and 1,500, $3,700 you borrowed, and you return $2,000 already. So the difference, it will be equal to $1,700. Okay, so you can see from here that how we can actually calculate that how much is a compound interest we have to give on the loan, and if we want to negate some of the effect of the interest, then how we can do this thing. Okay, note, because of the interest paid to the bank, the borrower repaid a total of 1358, which is equal to 3058 minus 70, more than was borrowed from the bank. Okay, so this is the profit basically the bank earned from you, from the loan or the interest that you give to the bank. Okay, now let us see this one, calculations with the cash flow diagram. So some of the more calculations that you can see here. So in the year 0, you have spent $5,000, or you borrowed that $5,000, then you borrowed $1,000, then you borrowed $2,000. In fourth year you returned $3,000. Okay, so this kind of event, we have to see that how much amount of money you are borrowing in the given time period and how much you are basically returning back. Okay, invest 5,000, 1,000, 2,000 at the end of 0, 1, 3 years, and take 3,000 at the end of 4 years. How much in account at the end of 7 if the interest rate is 8%? Okay, so you have to see that at the end of 7 years, if the interest rate is 8%, then how much you have to return. Okay, so simply you have to use a similar equation again, f of 7. So $5,000, you have this one $5,000 here. So at the end of 7 years, how much you have to return from 1 to 7? So the power of n, it will be 7. Okay, then again for this one $1,000, so you would keep it for the 6 years at least. Okay, so the power, it will be 6 here, and the interest rate, you can see this on the formula for the compound interest here. And the same way, $2,000, you can keep this one for 4 years. Okay, from year 4, 5, 6 and 7. Okay, so you can have the value 4 here. And similarly this one $3,000 that you have returned, so you have to minimize this payment along with the compound interest that you have already calculated for these payments. Okay, so $3,000, and you have like 3 years ahead. Okay, so minus 3,000, 1 plus 0.08 with the power 3. So the F7, it will be equal to $9,097 for the final payment F7. Okay, so this value, it will be $9,097. What would investment at 0 year be, get this amount at 7 years? Okay, now what should be the value, what should be the investment you would have made in the 0 year if you want to simply get this much amount of money at the end of 7 years? So the equation is simple that you can use here. So you have to use the simple compound equation, compound interest equation, which is equal to f, that is equal to p multiplied by I 1 plus I with the power n. So you can rearrange the equation in terms of p. Okay, so f will be divided by 1 plus in. So value of f you have already calculated here. 1 plus interest that is given here 0.8%. Okay, 8% basically, and the number of years 7, so you can get the value for the principal or the so the initial payment or the investment payment, it was $5,308. Okay, so from here we can see that we can say that P is the present value, or we can say the invested value. F is the final payment or the payment that we get after the number of years that can be mentioned with this F. Okay, so you have to be careful when you use the compound interest equation, and you have to see that how much a number of years you have to keep the money, and if you are returning some money, then you have how you have to compensate that effect. Okay, so this example is very simple and quite understandable. Okay, now let us talk about the annuities. Okay, so annuities, it basically it is a series of maybe it is a series of the uniform cash transactions of each of the value that you can have here taking place at the end of the each of the year. Okay, so this is basically the pattern that can show you the annuity. So in the simple words, you can take the annuity as the fixed amount of money that you pay or you get back in the form of installment maybe. Okay, so if you take some loan from the bank and every month you are returning 500 real, so every month it will be 500 real, that comes under the category of the annuity. So in the annuity, it basically give you the series on how much you can handle the cash by including whatever the interest rate. Okay, so simply the banks, they operate on the same formula. You take the loan and they give you like in 3 years time, you every month you have to return the same amount of money until 6 years. Okay, or the 3 years. So let us see what we have here. What is the future value, Fn? So Fn, it basically represent you the future value. Okay, A represent you the installment, you can say in simple words, or the annuity. 1 plus I is the interest rate, and is the number of years. Okay, so with the growing number of years, you can have the value for the future value or the final value. Okay, so if the value, if you took the loan for 2 years, so maybe the value of F n would be 2 here, and then if you have to return like $300 every month as an installment, so the A value will be the 300, and similarly the interest rate that is given to you, that is here, and n represent you the number of years. Okay, so depending on the value of n, you can see this equation. Okay, so if we simplify this equation in the form of geometric progression, this equation can be also used. Okay, so Fn, it is the final value, A is the annuity or the monthly or the annual installment that is fixed for the given time period. Okay, 1 plus I is the interest rate. Okay, and is the number of years, and I is the interest rate. Okay, so if you want to calculate that, if you are having some final amount of money that you want to return, and you know what is an interest rate and the number of years, then you can actually calculate what is the annual and or the monthly in annuity for your deal. Okay, so this is the equation actually we can use mostly to calculate the installment that we want to return to the company or to the banks. Okay, now let us see this one, discount factors here. Just a shorthand symbol for the formula in I and N. So if you are if you know what how many number of years you are dealing with and what is an interest rate, then you can actually calculate what is the monthly or the annual installment or the annual annuity. Okay, now this is a simple equation. Basically it represents you the compound interest equation. Okay, so simply this equation has been rearranged. Okay, so the final value, it is equal to the present value multiplied by 1 plus in. Okay, so you would be getting the same value here. Now there could be different things that you can deal with. Okay, so for example, if I take you to this table, if you have some information on the present value and you want to calculate the future value, then you can simply use the equation for the compound interest. Okay, if you are having the future value, okay, if you like this one, okay, if you want to or do some conversion from the future value to the present value, then what you can do, you should use this equation, or you can simply relate these two equations. So how you can relate this equation? P divided by F, that is equal to 1 divided by 1 plus I with the power n. Okay, and then you can multiply the f on the right hand side and you can rearrange the equation to get the value for the p. Similarly, if the annual or the annuity is given to you and you want to calculate the like the future value, then you can use this equation. So f divided by a, it will be equal to this part of the equation, and then you can simply rearrange the equation to find out the unknown. Similarly, this one f2a, which is the future value or the final value with the comparison of the annuity. Okay, so you can have an equation in the form of a divided by f, that is equal to this part of the equation, and then you can rearrange the equation to get the value. Similarly, you can see p conversion to a, or the annuity conversion to the present value. Okay, so these are some of the equations that are provided to you, and simply you have to see that what is the requirement, and then you can use the relevant equation and rearrange the equation to get the required term. Okay, now let us solve this example. What should my annual monthly car payment be if the interest rate is 8% per annum compounded monthly for 5 years? Okay, now what information do we have in this example? We are provided with the present value, which is 20,000. Then the interest rate per annum 8% and compounded monthly, which means that the m value should be 12, and then for 5 years. Okay, so the n value is also given here. So we are provided with the present value, we are provided with the percentage, the number of years, and we have to calculate the annual annuity. Okay, so which equation you can use? Simply you can go to the table here and you can see that according to the data which information you can use. Okay, so if you look at this equation here, you are provided with the present value. Okay, and you have to calculate the annuity. So the equation, it would be equal to a divided by p, that is equal to I multiplied by 1 plus I with the power n, and 1 plus I n with power n minus 1. Okay, now in this equation, because you have to deal with the compounded monthly interest. Okay, so you have to include the factor m. Okay, so wherever you see the n, you have to multiply this one with the m, and wherever you see the I, you have to divide this one with the m. Okay, so this is the same case whenever you use these equations, and you have to convert the nominal interest into the compounded like the compounded interest, or the compounded monthly compounded, or the quarterly compounded. So what you have to do, you have to divide the I with the m, and you have to multiply n with the m. Okay, so then you can use this equation. Okay, so in this example there are two ways to solve this one. First one, we can simply use this equation 9.13, where you get the where you are having the value for the p, and you can multiply the value p with this equation and divide the I with the m and multiply the n with the m. Okay, so you can get the value for the a, that comes out to be $405 directly. Okay, now there could be some other ways to solve the same problem. For example, maybe you can calculate the yeah, if you don't you can just like calculate the future value after maybe 5 years, and then you have this equation, and then you can use the future equation to get the value for the annuity. Okay, so you can use multiple equations here. So like you can use the equation number 1 here to get the future value, and then you can use this equation future value with the annuity. Okay, to get then you use this equation to get the annuity from that future value. Okay, so either you can use a direct equation, or you can follow any path that you want. Okay, but in all of these equations, what is the key point, that wherever you see I, you have to divide it with the m, and then wherever you see the n, you have to multiply this one with the m. Okay, so m, it basically represent you the compounded monthly interest. Okay, so if it is monthly, the value for m is 12. It is quarterly, then you have to use the value 3. It is like the if it is after 6 months, then you have to use the value 6. Okay, so you have to be careful when you choose the value for them. Okay, so this is the indirect way, and the direct equation that you can use, it is the equation 9.13. Okay, now let us solve this example which is about calculation of the present value, and it is very interesting. And let's see, you have just won $2 million in a Texas lottery as one of the 7 winners, splitting up to jackpot of $14 million. Okay, it has been announced that each winner will receive $100,000 per year for the next 20 years. What is the equivalent present value of your earnings if you have a secure investment opportunity providing 9.5% per annum? Okay, now you have won $2 million from some lottery, and the company is willing to pay you $100,000 per year, and it will pay you in the next 20 years. Okay, so what you want, you went to some bank and they give you some investment option with an interest rate of 9.5%. Okay, so there is some error here, some typo. This is 9.5%, but the solution, it is according to 7.5%. Okay, so you can make this one according to 9.5%. So what we can actually do here, so the equation that we can use here, it is the equation 9.14. Okay, so what is 9.14 equation? See this one. Okay, so you are provided with the annual annuity, which is $100,000. Okay, then you are provided with the interest rate, that is with the typo, it is 7.5%. the value of n, it is 20. The value of m, what is the value of m here? Is it given? Okay, so it is no information on the value of the compounding monthly or yearly, it is not given, so the value can be taken as 1. Okay, so value for the m is 1, that should be multiplied with the n. I, you have to divide it, this one with the m again. Okay, so you can solve this equation and multiply this equation with the annual annuity $100,000, and then you can get the value for the present value. Okay, so if you solve this equation this way, so this one is the annuity, and this is equation with the percentage 0.075, and would be 20. Okay, and so on. So the present value for your $2 million, it will be $1,019,000. Okay, now what could actually happen? A present value of $1.019 million is equivalent to 20 years annuity of $100,000 per year, when the effective interest rate is 7.5%. Okay, so if you say to the lottery organizers that they can pay you $1.019 million today, they will not pay you. Okay, why? Because they can invest this money, and they can further get some interest out of that. Now let us solve this example 9.16. I invest money in a saving account that pays a nominal interest of 6% per annum, compounded monthly. I hope the account with the deposit $1,000 and then deposit $50 at the end of each month for the period of 2 years, followed by the monthly deposit of $100 for the following 3 years. What will be the value of my savings account be at the end of 5 years of the period? First, draw the discrete CFT. Although this CFT looks simple and complicated, it can be broken down into 3 sub-problems. Okay. Now, in the explanation, what you can see here, you have an annual interest which can be compounded monthly. Okay, 6% is the interest that can be compounded monthly. So you have invested $1,000 for the period of 5 years, then you and you have deposited $50 monthly for the period of 24 months, and that will stay there for 5 years. Okay, and then you at the year at the month 24 you deposit $100, and so on, you deposit it till the 60th month or the 5th year. So you have to calculate what should be the total savings that you can have at the end of 5 years. Okay, so the initial investment, that is the first part, $1,000, how much you can have the future value in 5 years. Then you deposit $50 for 24 months. Now what should be the value or the saving that you can get after the 5 years? Okay, similarly you deposit $100 after 2 years, so what should be the saving that you can get at the end of 5 years? Okay, so the 24 monthly investments of $50, that is the second part, and the 36 monthly investment of $100, that is a third part. Okay, now You have to use the simple equations that we studied in the table 9.1. So the first part, that when you deposit $1,000, so what should be the value or the saving that you can have at the end of 5 years? So simply you can use the formula here from the table, that is the equation 9.5. Okay, so simply you go there, the simple compound equation. So value for 1, and what is an interest, it is given to you in the question, although you have to convert this one into the effective interest, and the value for n, that is the number of years. Okay, so as I told you, whenever you see I here in this equation, you have to divide this one with the monthly or the compounded monthly value for the m. Okay, so this one, in this question, the value for m, it is compounded monthly, so you have to divide it with the 12. Okay, so there are two ways: either you divide in this equation I with the 12 and multiply n with the m, or you can do the simple way that you calculate a factor here. Effective monthly interest, you divide 0.06 interest with the 12, that will be giving you the value for the effective interest rate. And here, instead of n multiply by m, so you can just simply write down the months that you have. Okay, so that is 60 here. So simply, if we use this equation 9.5 for this first part, you can get this equation: p multiply by 1 plus 0.005 with the power 60. Okay, so that will give you the interest or the future value from $1,000 investment. Now for the second part, you are doing this one annuity here for 24 months. Okay, so what we have to do here, we have to see the relevant equation that can give you the idea between the future value and the annuity. Okay, now annuity, we will go back to this equation, this table, and we will see this one, the equation, this one 9.11. Okay, so you have the value for the annuity, okay, $50, and you want to see what should be the future value, so you can use this equation. Now I, we have already calculated the value for the effective interest, that is 0.005, so you can use the value for I directly here. The value for n, okay, so n represent you the number of years, and we are dealing with the compounded monthly interest, so the value for n should be multiplied by m. Okay, so for 2 years, you have to multiply this one 2 with the 12, that will make 24 months. Okay, so that is equal to, we would say this one here, uh, p, that is, or this one is the annuity, then 1 plus I with the power 24 minus 1 divided by I. Okay, now this is the amount that of the value of when you invest this $50, and this is the value that you get after 24 months. Okay, now after 24 months, this value or this amount will be in the bank. Okay, so it is not out of the system. Now you have to calculate what should be the interest that you can earn for the rest 36 of the months. Okay, so simply you have to use the equation for the compound formula. Now what is that equation? P, that can be multiplied by the first one. Okay, now you have to calculate this one. You are provided with the present value, okay, at the end of 24 months, and then you have to calculate what is the future value. Okay, so you can multiply this p with this equation 1 plus I you have already calculated the effective interest, and n, it represent you the time that is after that 24 months, so that we have like 36 months, or you can multiply 2 with the 12 to get the value for the 36. Okay, the same way we have to use this one. The first part here, it will now become the p, and the second part here, it will become 1 plus I with the power 36. Okay, so this will combine, give you the value for the $50 annuity that you would make into the bank, and how much profit that you can made after 5 years. Okay, now the third part, it is quite simple. You invest $100 annuity monthly for 36 months. So simply you have to use the equation 9.1 again, this equation. Okay, so you have the annuity $100, and you have calculated the value for F. So simply you multiply the A with this equation. 1 plus interest, you have already calculated the effective interest, M, it can be 3 multiplied by 12, so that makes 36 months, and I, you have already calculated the effective interest, and then this one. Okay, so simply if you solve this part, so you would be having this part of the equation. So when you simplify this equation, the future value for this investment, it would be equal to $6,804. Okay, now this is one way of solving this example. Now there is another way of solving the same problem. Now what we are gonna do here, for the 1000, the equation is simple, as we have used this one. What is the total value for this $1,000 investment over the period of 5 years? Now what we do here, we take this $50 and we say that we invested this $50 for the period of 5 years. Okay, so we can get the value for this $50 investment for the period of 5 years, and then we see simply that what should be the value uh, or the gain that we can make from this $100 investment. Okay, so simply we can do this way. We have this one $1,000 P, and then a simple compound formula 1 plus I with the power 60, 5 years. Okay, then for the second part we have an annuity here $50, and we make the investment, or we keep on adding $50 for 60 months. 60 months. Okay, so that is 1 plus I with the power 60 minus 1, and then we can divide it with the I. And for the last part we say, okay, we like for the half of the part we take into this category, the category number 2, and the last half part we can again say, okay, we can have the $50 investment again in the last 3 years. Okay, so here $50, then 1 plus I with the power 36 months minus 1 divided by 0.005. So that makes the value 6804. Okay, so the result is same as before. So you can solve it either way, the way you like more, or the way it is more simpler for you, but it should not change the result, because the overall calculation and the steps, it will remain same. Okay, so the main thing from the today's lecture, that how we can actually use this table. So if you are familiar with using this table, then the calculation for the cash flow, it would be very much easier for you. So you should be able to see what should be this symbol here. Okay, and how you can relate this one with the formula, and what should be the value for n. If there is a value, if there is any compounded monthly interest, then you have to divide it with the m, or you have to, and then you have to multiply the n with the m also. Okay, or you can calculate the value for I in terms of effective interest rate, and in terms of n you have to use the value for the total month.